Good morning, everyone. We may have a little bit of a smaller crowd today. I think a couple of folks are working on trying to help DreamHost fix their Ceph cluster, which coincidentally is why the web page is still not working. And Sam is also out this week on vacation, so might be a little bit of a quick meeting, but we'll see. Let's see what is going on this week in pull requests. There's just two new kind of interesting ones this week, but both are good. One is Ramesh has been working on the memdb store interface, basically storing key value stores in or key value data in memory structure, and that he's switching from a B-tree implementation to generic maps just because the B-tree implementation was actually not performing very well. So that'll be interesting to see how much that improves things. But yeah, he's working on that. And the other one is that Dan Lambright has a first attempt at using RCU locking for, I think it was, is it PG info that he was doing? PG map. And that's really exciting because I think once he starts kind of getting that working, there's a number of places we might be able to use it. The big thing that I'm hoping for is that we'll be able to speed up fast dispatch with this, but I guess we'll see. That's 11.393 if anyone is interested in playing around or testing it, although I'm not sure if it actually works yet or not. So those were kind of the two new interesting ones that are there this week. A couple of different things closed. Most of it was Blue Store related. There's been a lot of work on, excuse me, reducing the size of the in-memory structures for blobs and extents and other things like this. So a lot of the stuff this week that closed was related to work in that area, and it has been helping. We have been kind of slowly reducing the amount of memory required to cache O nodes. And that's kind of been a big focus for the last week or two here. And in general, we're also reducing the number of cached O nodes. Once the stuff that Alan and Sage have been working on for the mempool work can merge, hopefully we'll be able to change it from requiring that people say how many O nodes they want to cache to something more like how much memory they want to use for cache per OSD. And I think that's going to be a really important thing for us to be able to do before kind of unleashing Blue Store on the masses, just because it's pretty tough to tune right now based on kind of the variable size that these data structures can have depending on things like the min-alloc size. So yeah, just lots of work in that area. Let's see. I think for updated ones, it's like 11.213. I'm hoping that we can get that merged soon. That's really nice. It reduces the size of PG info and kind of, or at least reduces the amount of data that we write every time by kind of not lazily, but more seldomly updating a lot of fields that don't really matter that much. So that's really good. For Blue Store, that actually improves smaller random write performance pretty dramatically. And again, is much less overhead on RocksDB, which is always good. I think we're trying to get the fast encoding stuff merged, but there are conflicts, so Sage will have to look at that one. And that's kind of basically it. So any questions on any of the pull requests? All right, well then moving on. So for Blue Store performance this week, I sent out just kind of an email to the mailing list with some different graphs, and I suppose I could pull it up here if anyone actually wants to look at this thing. 1 second. See if I can share my screen. Can you guys see my screen right now?
Yes.
Okay, good deal. So, kind of the biggest issue I see right now with Blue Store in terms of kind of how we're doing relative to file stores with sequential reads, small sequential reads, and you know, this is one of those things where hopefully you don't see it that often. You know, if programs are doing small sequential reads, it's, you know, they're probably not that well written, but it kind of looks bad from the standpoint that, you know, if someone does benchmarking, it's going to look a lot worse. So here, this is kind of the percentile difference graph I've got showing kind of where File Store was at Joule, where Blue Store was at Joule, where each of them are now, and then what happens when we change the min-alloc size on, this is with NVMe devices, but when we increase it, and you can kind of see here that we're not doing so great with Blue Store, and we're doing quite a bit worse actually than we were with Joule in master. If we increase the min-alloc size, it does help pretty dramatically. You can see that anything less than 16K all of a sudden kind of jumps up compared to what happens if you leave it at the default 4K. Kind of the question here is how much is this due to fragmentation versus how much of this is due to these all kind of being sequential and synchronous. So that's something that we probably need to look at here in the coming weeks. Sage has some ideas for how we might be able to fix it, but it sounds like it's going to be a lot of work. So, unfortunately,
do we understand what the problem is?
Well, that's exactly it, right? I mean, if it's fragmentation, then it might be that just increasing the min-alloc size will help this and make it better. And one thing in Blue Store and Joule is that the default min-alloc size for SSDs was 64K. So that might explain why in Joule we were seeing a higher sequential read throughput in this test. It's on the list of things to test again, to go back and look at that. But I think that might, I guess, if that's the case, right, then that means it's probably fragmentation. But you know, potentially there might be other things here going on too. So I don't know. What are your thoughts, Alan?
Well, I think that the history of storage devices suggests that we're going to end up having to go tackle compaction or, you know, defragmentation, whatever you call it, eventually.
Yeah.
You know, I mean, even with XFS, which is a pretty advanced file system, if you talk to the users, they'll tell you that you really end up having to defragment the product over time. And
yeah.
I suspect that we're going to have the same issue with Blue Store at the end of the day. Changing the allocation size, sort of, you're trading off one problem for a different problem when you do that.
I agree. But at the same time, right now, it's looking like with a small min-alloc size, we're generating so much metadata, even with all of our improvements that we made, that we're hammering RocksDB, kind of to the point where doing the extra write ahead log write is actually cheaper than dealing with all the metadata. So there's multiple aspects to this, right? There are multiple trade-offs that we have to think about.
Well, do we know that that's what's actually happening?
What we've seen kind of in the past is that RocksDB, when you have a small min-alloc size, there's so many blobs and so many extents that are getting kind of shoved into it that the write amplification and compaction overhead just kind of starts killing things. There's lots of reads on the DB partition. There's lots of writes on the DB partition. The write ahead log itself is kind of relatively minor compared to what's happening on the DB partitions.
Yeah, and basically I'm seeing around 2.5x more write if I have like min-alloc size of 4K. Yes, in min-alloc size of 16K, we have like one giant write of like 4K that is going to the wall. So if you don't consider that it is leaking into the SST files, so the amount of write going to the SST files is really small. It's around 500 bytes, 600 bytes versus probably 1.5K in case of 4K min-alloc size. That I verified with long run 10 hours run, and that's why it's helping. Even with the default settings of the RocksDB, it's helping the performance boost around 30% or so.
Well, it does shed light on the hypothesis about what's going wrong. I guess the question is what are the proposed workarounds for it? I mean,
yeah. Well, I mean, to be honest, I mean, I think part of it might be that we need to consider key value stores that have less write amplification and less compaction overhead. I mean, that might be. We'll see. Maybe we can tweak RocksDB in ways that we don't understand yet to avoid some of this, and maybe we can continue to shrink the amount of data that is in the O nodes, right? Maybe with all of these things together, we can get to the point where we're actually better off not doing the write ahead log write as opposed to the increase in metadata. But it doesn't seem like we're there yet, just based on kind of what Somnath has seen and what I've seen. It looks like we're actually better off eating the extra
right. Well,
write ahead log.
Right. What you're saying, right? So what you're saying, strongly suggests that it's not the write ahead log write that's the issue. It's the coalescing of multiple transactions to reduce the blob and the extent map sizes.
Well, it's the reduction in the number of extents, right? Because when you increase the min-alloc size, yeah, you have fewer.
Right.
There's like 4x
exactly.
fewer.
So I mean, this all strongly suggests is supporting data for that hypothesis. Okay, so the question is if that's really what's going on, then that suggests to me, more likely that the allocation policy itself is flawed.
Sure. That would be difficult to fix, though. I'm not sure how I could. Well, what do you think? I mean, I guess I don't see a way to do it better, but I might not be. Yeah, tell me what do you think?
Well, I mean, at the end of the day, to get to the nirvana, you want small structures in the metadata, which requires that you're going to coalesce multiple small writes into sequential places on your storage medium. Now, the write-ahead log is one way of doing that, but clever usage, of allocation strategies might do the same for you, in the sense that if you have multiple streams where you're fetching or where you're storing data, if you sort of left space, so to speak, for them under the assumption that's what was going on, you would achieve the same thing. That makes sense?
Kind of in a very high level hand wavy sort of way. I don't.
Agreed.
Yeah.
Again, it's another trade-off. If what you do is you say, okay, I'm going to spread the writes around and leave a lot of space around them in the hope that having written this, he's going to come by later on and do another sequential write, and I'll have a place to put it so that I don't have to expand the extent structure. That will dramatically improve this case running on flash. It's a disaster on hard drives.
Yeah.
Okay.
Yeah.
And it probably indirectly will contribute to more fragmentation in other patterns that are sort of difficult to predict, I think.
Yeah. I will say it concerns me, but maybe.
There are other potential solutions for this problem. So, for example, what you could do would be to go ahead and allocate large chunks of space and do direct writing and keep track of the extras. And if the extra space wasn't consumed in some appropriate interval, you'd go back and reclaim it. There's all sorts of strategies you could think of.
Yeah. It sounds complicated, but
yeah,
I think you're right.
That's kind of the inverse of the write-ahead log, which is sort of, instead of leaving the data there, you leave an annotation that I've allocated more space than I needed for this, and if you limited the number of those, you could go back and clean that up.
I guess the thought I have though is that, like, as we progress here with storage technology, we're starting to see like NVRAM become more accessible to people, and other really fast small amounts of memory, right, that persist. So is the write-ahead log really a bad solution if you potentially have a small pool of really fast persistent memory you can target for it?
Well, no, that's exactly right, which is that most high-performance storage systems have a small scratch pad of persistent memory for exactly this reason.
Mm-hmm.
Of course, once you admit you have that, then it turns out that RocksDB might not be the best database either. But that's another story entirely.
Yep. No, I agree. I would like to see us really not dependent on any particular key value store implementation.
Well, that's a great theory, but it's not going to work out that way.
Yeah.
The reality here is that we're engaged in a bunch of optimizations because of it.
Yeah. On the plus side, though, at least with something like a write-ahead log, it's not that complicated, right? That piece is less hard to send
the question of what you put in the write-ahead log versus what you dump, directly is deeply affected by the mechanics of your database. That's basically what we're struggling with here.
Yeah. Fair enough. Well, let's continue through some of these numbers so that we can actually see some of this other stuff. So for sequential writes, we're doing beautifully right now, at least in the test that I've seen.
You mean large sequential writes?
and small sequential writes, not reads, but writes here. For basically all sequential writes, recent BlueStore and all the tests I've done look good.
Oh, I'm sorry. We were looking at sequential reads before. Is that it?
Yes, we were looking at
Okay.
sequential
I
reads
apologize.
before.
Okay.
Yeah, no worries. So yeah, for sequential writes, we're doing really good. Joule, we were bad for various reasons, but everything recent we're better than file store. And for large sequential writes, we've always been better, just because that's kind of the whole benefit of the way the BlueStore is written.
Yeah, we're still not getting to 100% better, which is what you would expect, right?
Well, would you really expect? I mean, that would be the upper bound, right?
Right. But you should be getting pretty damn close if your writes are large enough. I mean, if you're doing 4 megabyte writes and the metadata overhead is 3 or 4 kilobyte chunks, you're dealing with 0.3%, right?
Yeah.
0.4%.
Keep in mind though, this is with replication though, so there is that extra step involved here, no matter which backend you're using. It's re-replicating out to the secondaries.
Are you CPU limited or network limited?
Not CPU limited, but I mean, there's
if you're not CPU or network limited, then replication has no effect on the local node. I mean,
well, there's going to be some extra latency and potentially some.
Right, but if you're not CPU limited and you're not network limited, then that extra is sort of noise.
Yeah, maybe.
Yeah. I mean, it would show up in latency, but not in throughput.
Mm-hmm. Could be that we're hitting some of the different buffer limits that we have in places, though.
Well, there could be lots of things, but my point is that replication is not a good explanation for not getting to 99.7% improvement.
I have a suspicion that it might be a valid explanation for some of this, though. It'd be interesting to do a single OSD test and actually see. I suspect that we'll actually get closer, but that's just a guess.
I wouldn't be at all surprised to find out that there were serializations that occur because of replication that are indirectly preventing you from obtaining enough parallelism to saturate the CPU. In essence, you don't have enough queue depth or enough parallelism in various stages of the OSD. And if that's what and if the single OSD experiment shows that, it gets to, it gets to the 99% that you would expect, and the other one doesn't, but you're not network or CPU limited, then we've got code to go fix.
Mm-hmm.
Or translation, you have more performance that you could get.
Yeah. One thing I have noticed is that for large sequential writes, there's a lot more variability and noise at the upper end. So like with file store, we're basically, we're eliminating all that noise because it's basically artificially, limiting it, right? Whereas with BlueStore, when we get up there, we're seeing a fair amount of variability in the throughput at kind of the the upper end. I mean, you can see it in those lines, right? We're seeing there's very little difference about sequential write behavior in Joule, BlueStore, and recent master BlueStore, but you see those at like 4 megabyte IO sizes there.
The shape of this graph is just wrong. I mean, if you think about it.
Which one?
The sequential write. As the block size gets. Well, the progression from. Oh, wait a minute. I'm sorry. This is a difference. Okay.
I've got the actual. If we scroll over, you can see here's what the actual throughput graphs look like.
Yeah, that doesn't make sense. There's something else going on in the system. You're not hardware limited here.
Yeah, probably not.
Right. I guess
In
if
any
you're not
event,
hardware
though,
limited anywhere.
we probably are on the file store side
Yeah.
because there you're doing the extra write, so you've maxed out the device.
Yeah. Well, yeah, I would. Yeah. File store is the solid red line that's flat.
Yep. So basically, what?
Does that really make sense?
Yeah, it does. Basically, you're doing twice as many writes, so you've hit basically that is right around where what you'd expect the hardware limit to be right there. And now we are not
Yeah.
hitting
Okay.
any of the software limits that
Yeah.
exist
I'll
once
buy
we
it.
stop doing that
Right.
extra write.
Because you're using the buffer cache to coalesce the writes.
Yep.
Yeah. Okay.
And with Blue Store, we're not doing extra writes, so we're more efficient. But now we're starting to hit some of the various software inefficiencies that we have somewhere.
Right. Because, if you were solely hardware limited, the shape of that graph would be different.
Yeah. But the good news, right, though, is that in recent versions of Blue Store, we're still always better than File Store was. So,
Yeah, I don't think
it's maybe now we're.
That's not much of
What
a
was that?
metric, guys. That's not much of a metric of success.
Well, I don't know. I mean, like, okay, we're
I'm
almost.
sorry.
Yeah.
Okay, I mean, realistically, in the competitive world, nobody's going to care about how you do relative to file store. They're going to care how much out of the hardware you extract.
Yeah.
Okay.
Sure.
And what these graphs tell me is that there's still some kind of plumbing problem internally in the OSD. Might not be Blue Store, it might be elsewhere.
Yeah.
Okay, but there's some kind of plumbing problem because the shape of this graph, if you think about that as the block sizes increase, it should spike up to the 100% on the difference and then flatline pretty quickly. Because as each IO size gets bigger, the CPU the metadata overhead is constant. So as the IOs get larger, you see less and less of that.
Yeah. We should in this case be seeing some amount of metadata overhead. So we probably won't hit quite exactly 100%
Agreed.
100% doubling. Right?
You'll only approach them. Well, but I don't know if that's true because file store has metadata overhead also.
It does, but I would think that it's probably, well, maybe it's not less. I don't know.
I bet it's not less. But I mean, the point is that any account, I mean, the metadata is only going to be a few, at most a percent or two when you're doing 4 meg IOs. I mean, any way you slice it, even a lousy metadata implementation struggles to get to 1%. Okay, because 1% is what, 40K for a 4 meg IO. Okay. Okay, 2%. I mean, if you're not into the high 90s here, the metadata overhead is not an explanation of what's going on.
Even with SSD and NVMe, though, 4K writes are going to hurt you more than than the relative fraction of the total throughput, right?
Agreed. Agreed. So instead of heading, if you're just going to count the IOs and you're going to say that the small random ones count more, if they're 2 or 3x the cost, which is not unreasonable, okay, now you're at 95%. But you're struggling here to get to 60 and 70%.
Well, we're at probably about 75 to 80% of the available.
I understand that. What I'm saying is you should be, in the 90s.
Sure.
In other words, there's like another 20% performance yet to be had.
Yeah, I would probably agree with that.
Yeah.
So, Mark, what is the difference between file store VIP and file store Jewel?
Oh, just the Jewel is the Jewel release, and then this is the work in progress release based on a recent master from like last week. So basically, the whip version of FileStore here is using the async messenger, whereas the Joule one is not. And there's probably a bunch of other random stuff that's in the work in progress one, although the async messenger is probably the biggest difference between them.
The Joule one is
There may be other things.
giving much higher performance than the whip, right? With FileStore.
In the sequential write case, they're exactly the same. You can't see it, but
Okay.
the lines just overlap each other.
Oh, okay.
All right, let's move on then to random reads. So in the random read case, what you're seeing here, this big dramatic drop, is entirely due to async messenger. It happens both with FileStore and with BlueStore. So BlueStore itself is not really causing much of this. We see in the Joule version of BlueStore, it was doing a little worse maybe than FileStore. But in fact, with BlueStore, well, again, this might be async messenger. We're actually doing a little bit better at like 128K to maybe like 2048K reads. The good news is that this can be mitigated quite a bit by using the setting this, I think it's send inline to false in async messenger. That helps quite a bit. Probably the other thing that needs to be done here is speeding up fast dispatch. So we're going to probably, if nothing else is done, we're probably, even with send inline false, going to be seeing maybe a 10% performance regression for random reads at small I/O sizes. It's not going to be as bad as what you're seeing here, but we may still see one. We still may see a bump here at like 128K plus I/O sizes though, so it's a little offset, but it'd be sure nice if we didn't see that small random read regression. So we'll see. We'll see if anything else can be done in the meantime. Dan is working on these RCU work for different locks that we have in place, and maybe that will happen faster than kind of Sam was expecting. I'm not sure.
Excuse me.
Yes.
So I'm looking at the BlueStore Joule, all the data you just presented for the sequential and the random. It kind of suggested that there's a dramatic change when you are at the IOPS size of 32. If you look overall, yeah, the 32, the changes,
Okay.
dramatic changes are all from the 32, right?
Yeah, and that was kind of the old. So like in the sequential read starting out up here, there's kind of
and
that
then
yellow
it
line
changed to the better. Yeah, it either go to the better directions or the worst direction at 32, right? For your sequential, if you see sequential read and write from the 32, it started to increase, right? But for your random read and random write, random read start from 32, you decrease. And then for your random write, start from 30 random write. Can you go down more?
So
I can't
like
see the graph on my screen. This is sequential,
okay.
right? Yeah, random write
Yeah.
again from 32, you increase. From the turning point is at 32. It's a commonality from your data.
And that version that you're seeing, that yellow line, that's actually the old version of BlueStore from the Joule release. So like the green line and the kind of purple line and the blue line are actually the most recent version of Joule and Master. So what you're seeing
those
there
are already released on in the web. I mean, it's already available.
It's only available in the development version that's in GitHub. So it's not
because now
available
I'm
as
using
a
the Joule. Yeah, I'm using the Joule. Yeah.
So a lot of the changes since Joule have been focused on improving the way that we handle metadata in BlueStore. And I think a lot of what you're seeing there is kind of related to that. There's some other things that have been going on too. In fact, it's hard to remember exactly everything that's gone in since Joule, but kind of the goal in the last couple of months here has been to kind of eliminate problems like this one that you're seeing with the random write performance, where we're dipping way down, and then maybe we're improving, but maybe not. There's actually been some intermediate releases here where the random write performance actually looked really, really bad. But the good news here is that like especially with random writes, if you look kind of here at the IOPS graph, you can see that for Blue Store, no matter if we're using like a 4K allocation, like in this green line, or if we're using a 16K min allocation, which is kind of our proposed maybe idea for the release here, we're actually consistently above file store. There's kind of this little weird dip at 8K here, but overall we're doing better. So that's good. I mean, that's what we were hoping to do over the last couple of months here is basically really show up the random write performance. The things that we really need to look at here now going forward are going to be, I think, if there's anything that we can do to kind of bump async messenger to be a little faster, to get it kind of over this 4K random read regression that we're seeing. And again, it's not as bad as it looks here, but we still have a little bit of one. Otherwise, we may want to think about the trade-off that we're taking versus simple messenger, or at least instruct our users to think carefully about that. And then also the sequential read issue. That's the one that looks the worst, right? I mean, even though small sequential reads probably aren't something that you hope a lot of applications are doing, that's the one that you know, if you're benchmarking, it really sticks out. So the kind of the last two here with sequential mixed read write graphs, it kind of tends to follow the first one. The read performance, the sequential read performance regression for small IOs just kind of sticks out here. It's not as pronounced, but it still happens. But our sequential write benefit is helping at large IO sizes, so that's why it's kind of almost a mix of the two. We see the large writes really helping out at large sizes, and then we see the small sequential read performance really hurting us at small sizes here. And random read write again is kind of follows the others because of the issue with async messenger. We're seeing small IO kind of dropping down, but the writes help pull us up. So anyway, that's kind of where we're at with it. My personal take on this is that we need to be looking carefully at the allocation size that we use. I'm guessing 16K is where we want to start out right now, just to kind of as an interim thing until we can make smaller allocation min-alloc sizes work better, either through less metadata or whatever, and it will help with fragmentation too. And then we need to look at the sequential read issue, figure out if it's fragmentation, figure out if some kind of async support for pulling in multiple extents at once from the one data structure, or doing async reads in general. I'm not sure what Sage exactly wants to do there, but I think he's got ideas. So that's another big thing. And then kind of anything that we can do with fast dispatch and async messenger to kind of get it over that last little hurdle. I think that would be very good. So those are kind of the priorities I see.
Is this file, data file shareable?
Yeah, it's on the mailing list. Yeah.
Okay.
Let me get the link here. I'll stop sharing this. Unless, is there anything anyone else wanted to ask about the graphs?
Welcome back, Will.
Okay, here, I'm gonna stop sharing my screen then, and I'll put a link to the mailing list post in the chat window. There we go. Let's see now. I need to go find the agenda. Performance weekly. Okay, the only other thing I guess I had to talk about then was that we are also looking at how to tune RocksDB's write-ahead log. And unfortunately, our test lab is sort of broken right now since the DreamHost has been having some problems that's affected the DNS server and some other things. But I did get some initial results, and kind of the what I'm seeing so far, the trend I'm seeing is that basically just increasing either the number of logs or the size of the write-ahead logs in RocksDB seems to help kind of stabilize the long-term performance in the tests I did. Now, these are only 1-hour tests as opposed to like the 10-hour tests that Somnath has been doing. So it may be that we need to make sure that it doesn't hurt us in really long tests, but at least for these 1-hour tests, it seems like larger log sizes or more logs tend to help kind of even things out and avoid.
Mark,
yeah.
If I understand the way BlueFS works, he basically can distinguish compaction I/O from the other IOs that are going on. Do we keep a different set of stats in there so that we can tell during these runs, what's going on in the compaction world?
Yeah, you're talking about when RocksDB compacts, telling whether or not it's compacting metadata versus compacting like write-ahead log writes that have propagated into level 0?
Yeah, basically the level 0 writes are distinguishable from the background compaction action. Okay, and if we're going to monkey around with these files, I don't think it takes a lot of work to sort of figure out how much I/O gives you how much RocksDB I/O, and what I'm saying is I think we have the ability to move to a situation where some of these tunables are more science because we have a deep instrumentation into what's going on, and to be able to discern, for example, whether your 1-hour run is actually triggering any compaction. As opposed to, say, the 10-hour run, which we know would be, as well as being able to determine, dynamically when in performance that we're in the middle of doing compaction, and that's why the performance is dropping, etc.
Yeah, we're absolutely triggering compaction easily within a 1-hour run. We see compaction happening, or at least in the test that I was doing earlier. The compaction was happening probably on the order of maybe like every 40 seconds.
Mm-hmm. Well, but do we, for example, track the kind of write amp that we're seeing? I mean, we have the ability to actually compute the actual write amp that we're seeing through RocksDB.
Yeah, and actually RocksDB will record its own write amp, so you do get that. I think the trick here, though, is when we are doing write-ahead log writes, based on kind of some of these parameters that you have that you can tweak, you may potentially be leaking them down into level 0, at which point they may even get compacted into level 1, depending on kind of how short-lived versus how long-lived they are, and kind of how the moon and the stars line up regarding compaction. So that's something that I think we need to understand better is when you have a small, like a 4K min-alloc size, right? You're not really doing while writes anymore for most of these kinds of IOs anyway. So you're not going to have any leakage, but you now have much bigger metadata structures to deal with. You have many more O-nodes to deal, or not O-nodes, but you have many more expense to deal with. So
I understand that. I'm just saying that
yep.
These are all qualitative phenomenon that we know exist. And and I guess the question I was asking is, do we have full instrumentation to be able to quantify these qualitative behaviors?
No, I don't think we do. I mean, it would be really, really good if we could differentiate write-ahead log data in the SST files versus versus metadata, but I don't think we have any tools right now that actually do that.
Well, but I think we know what we're putting in there. I mean, it should be trivial for us to keep track of that, is the point I'm making.
Well, we don't know though how good RocksDB is at making sure that write-ahead log writes don't actually propagate into the mem tables versus into the log. We think it's pretty low, probably, but we don't know it for sure. Does that make sense?
I understand what you're saying. What I'm suggesting is that with the right instrumentation, I think we have the ability to collect all the information that we need in order to prove or disprove whether, you know, the assertion about how efficient RocksDB is at handling the write-ahead log entries. I mean, I agree with you. I mean, if we are not diligent at pulling write-ahead log entries out of RocksDB, it's a chance that he will merge them into his SST files, you know, and you'll see, you know, an increase in write amplification there. There's no question about that. But I suspect that we know what we're putting in the front, and we can see what comes out the back. You know, if you're leaking these write-ahead log entries, you know, those are so large relative to the other things that are going on. I think you're going to see it pretty directly in the statistics if we're tracking them.
And I don't think that we are tracking that exactly yet.
Right, and what I'm saying is that I think if we put a little bit of diligence into tracking those, a number of these hypothetical scenarios can be sort of proved or disproved with actual quantitative information pretty quickly.
I don't disagree, Alan. I personally, I think, would like to see us maybe go more down that route as opposed to just kind of blindly tweaking RocksDB options, or not blindly, but maybe, you know, semi.
Yes. Yeah. In other words, I agree with you. I think the reality is if you don't get the maximum instrumentation, you're just firing blind. Okay. And who knows what you're going to hit.
Yeah. The good news, though, it hasn't been entirely fruitless because, I mean, the trend that seems to be showing up is that we do better with larger write-ahead logs, which kind of makes intuitive sense, right? The trade-off is then the question of, you know, that uses more memory. So, you know, do we trade the memory for having the larger log and the better, more consistent performance by having more write-ahead logs?
So you say you do better. You say you do better, but in which test cases? I mean, random.
So like 4K random writes.
Yeah. So I would reject that. I don't understand why the log file, as long as you assume that the write-ahead log entries are purged from RocksDB reasonably quickly, you know, well less than the size of a log file, then I don't understand why there's any correlation between the size of the log file and the performance. If anything, I would argue it'll get worse because your in-memory lookups will get longer and larger.
They do get larger and longer, but if you are to the point where you're in the middle of flush and you have filled up any log files that are not anything that's not flushing, right? If you've gotten to the point where anything that was available to you is now full and you're in the middle of flushing the other ones, now you've blocked writes. And that's the behavior that we see, is that we see these weird stalls where all writes stop. And it seems like it may be related to the fact that we're now in the middle of flushing the write-ahead log. Or we're compacting in the SSTs, one of the two.
Well, okay, so if it's, well, you know, certainly the SSDs could be garbage collecting on you, and you might get some excursions there. And again, that, you know, by looking at the physical latencies, we should be able to see that. But I mean, the theory with RocksDB is that he never stalls the front end for the back end. Okay.
Yeah,
but,
and that's not entirely true, though, right?
Because eventually you have to run out of something. Okay. And his behavior, we may be driving him to that state.
Well, and compaction in level 0 in RocksDB is still single threaded. So, once if you're doing compaction, your write ahead log, I think, if I understand it correctly, is basically your only barrier towards not stalling.
Okay. Still seems to
I could be wrong, but that's my understanding of it.
Yeah, well, I'm not disagreeing with you. I'm just saying that I think that we should be focusing on better insight into the system rather than focusing on hypothetical what ifs.
Yeah, I agree with you, Alan. It takes time.
It does take time, but I submit it's the fastest way to the endpoint.
Sure.
Yeah, yes, it is a little tedious to go in and add a bunch of stats in there, and then you add some histograms or other analysis techniques. You'll burn a day or 2 or 3 to do that, but then you're in second gear when it comes to actually doing the performance analysis, because you'll actually see what's going on, and when and you'll be able to make tweaks and make rational inductions about how the system should behave, and prove or disprove that. I suspect we're going to find, like a lot of these things, that the knobs that are there and the documentation of them is subject to interpretation, and just because that's never happened with any of the Ceph knobs. Okay, and I'm going to grant them the same discretion. Okay, and you're going to find that until you have a deep understanding of what these knobs do, you're going to find you really don't understand how it works at all.
Yeah, I mean, we saw that with the. Oh yeah, I mean, we just saw this with all the metadata work, right? I mean, where the amount of in-memory data for metadata for the O nodes and for the blobs is huge. I mean, blobs are gigantic, and I think it's easy to overlook that if you don't actually instrument it.
Right, exactly. So I think we're a little lackadaisical about the instrumentation on these things.
Yep. Well, maybe that will be the next thing that we can focus on here then, is actually getting this stuff instrumented. The good news though is that we've actually on the metadata side, we actually the work that you and Sage did, getting all of that memory usage instrumented in WIP mempools is going to be really, really useful. I mean, that's fantastic. So we're making progress in this regard. It's just maybe we could do it faster. All right. Well, we're about out of time, guys. Was there any other kind of last minute things people wanted to talk about? All right. Well, then, everyone have a good week, and we will meet again next week. Thank you much, guys.
Thanks, Mark.